Thank you so much for the introduction and for the generous invitation to speak. Today, I'm going to share some joint work with two groups of authors. The first group is Bhargava and Shankar and myself, and the second group is Bhargava, Weiho, Shnidman, and myself. And the results I'll tell you about today have to do with second moments for two summer groups and two class groups of cubic fields and consequences thereof. Okay, so let's start um, with a discussion of some background material. A lot of this should be familiar, but I wanted to go over it in any case. So let's start by talking about elliptic curves over Q. So every elliptic curve over Q is isomorphic to a unique curve in the short Weierstrass form. So E can be written as EAB. The equation is of the form y squared equals x cubed plus ax plus b, where a and b are integers that are minimal in the sense that if p is a prime that divides a to degree 4, then p cannot divide b to degree 6. Because every elliptic curve has this nice form. And a natural question you might ask is, what is the set of rational points on the curve? And in this regard, we have the well-known theorem of Mordell, which states that the set of q rational points on an elliptic curve over Q forms a finitely generated abelian group. Okay, so I work in arithmetic statistics, so the question I'm interested in is how does the set of rational points vary as the elliptic curve varies? And more precisely, the question you might ask is, as E ranges through all elliptic curves over Q, what is the distribution of the rank of E of Q? Okay. In order to make sense of this question, we need to specify how we order elliptic curves, and we do so by the naive height. So the naive height of the curve EAB with the short Weierstrass form y squared equals x cubed plus ax plus b is just the maximum of 4a cubed and 27b squared. And you might recognize those two monomials as the two terms that comprise the formula for the discriminant of the curve. So that's the central question we're interested in. And now I'm going to introduce some notation. So if you have a function y on the set of elliptic curves over Q, we're going to define what it means to say the probability that y equals a and the average of y. So the probability that y equals a is obtained by looking at the probability that y equals a among elliptic curves of height up to x, and then taking a limit as x goes to infinity. And similarly for the average, you can define the average of y over curves of height up to x and take the limit as x goes to infinity. And of course, these quantities only make sense if these limits exist, which they a priori might not. More generally, we can make sense of the statement that the probability that y equals a is at most some b, or the average of y is at most some b, and in this case, we're just taking a lim sup as the height bound goes to infinity. And you can make sense of similar statements for other inequalities. Okay. Right, so that's just a bit of notation that we'll use very frequently in the talk. Okay, so then we have the following conjecture regarding the distribution of ranks of elliptic curves. So this is known as the minimalist conjecture. It's due to Goldfeld and Katz-Sarnak. So it states that when elliptic curves E over Q are ordered by height, we should expect that 50% of elliptic curves have rank 0 and 50% have rank 1. And moreover, that the average rank of elliptic curves should be 1/2. Okay. Something important to note about this conjecture is that the claims about the probabilities of rank 0 and rank 1 do not necessarily imply the claim about the average rank being 1/2. You might think that they do, but they don't. And the reason is that a priori you could have some kind of zero density set of curves where the rank grows so quickly that it contributes non-trivially to the average, even though it doesn't contribute to either of the probabilities. Now, if you knew, for example, that the second moment of the rank was finite, then this pathology cannot occur because if you have a zero density set of curves contributing non-trivially to the average rank, it'll contribute infinitely to the second moment. And more generally, if you knew that the mth moment of the rank was finite for every integer m at least 1, so in other words, we're saying that elliptic curves with rank bigger than 1 are extremely sparse, then the moments are determined entirely by the curves with rank 0 or 1. And in particular, you would find that every moment of the rank is equal to a half, not just the first moment. Okay, so that's just some remarks about this conjecture. The statements about probabilities are not, there's something additional that you need to be able to deduce the statements about moments of the rank from the probabilities. Okay, that's the conjecture. Now, as we all know, it's very hard to get our hands on the rank, but we can bound it using various techniques. And one of them is by using Selmer groups. So let me tell you a bit about Selmer groups. I'm not going to define them just yet. I will give the definition later, but for now, let P be a prime. Then the P-Selmer group of an elliptic curve E is a finite dimensional FP vector space that fits inside a short exact sequence. So this is the sequence, so the P-Selmer group's in the middle. On the left, we have the rational points of V mod P times the rational points of E. And then the co-kernel is the P torsion of this group, SHA E, which is the Tate-Shopper-Rayvich group of E. Okay, so why is this useful? I haven't defined the P-Selmer group, but nonetheless, you can see the use from the sequence. It follows that the P-Selmer rank is an upper bound on the rank of E of Q. And we can be a little bit more quantitative here. So there's a basic inequality which states that Px is less than or equal to P to the x for any integer x at least 1. So that implies that the P-Selmer rank of E is at most 1 over P times the size of the P-Selmer group. So that's a very simple bound. But what it means is that if you can bound moments of the size of the P-Selmer group, then you can bound moments of the rank. Okay. The advantage of using these Selmer groups is that they're more readily computable. And then it becomes a problem of interest in its own right to describe the distribution of Selmer groups of elliptic curves. So that leads us to the conjectural distribution, which was formulated by Poonen and Raines about 15 years ago. So they developed heuristics that predict the entire distribution of the P-Selmer groups of elliptic curves over global fields. So let me state, I guess, what their conjecture says. So they predict a precise formula for the probability that the P-Selmer rank is a given integer r. So that formula is here. And then on the next line, they also have a prediction for the mth moment of the size of the P-Selmer group. So this has a beautiful product formula. Product I goes from 1 up to m, 1 plus p to the I. And some remarks about this conjecture. It's expected to hold in actually quite general families of elliptic curves. So this is not just a conjecture for all elliptic curves over a field. I mean, it's, you could look at a subfamily of elliptic curves over Q, say, that are defined by finite sets of local conditions and even some infinite sets of local conditions. And this is the setting in which people like Bhargava, Shankar, Ho have been working and proven many results towards these heuristics in those cases. You could also look at quadratic twist families, and the conjecture is supposed to hold in that setting as well. And there we have many important works of Swinnerton, Dyer, Kane, Mazur, Rubin, Klagsbrun, Smith, and many others. In this talk, I'm going to focus on the case of subfamilies of elliptic curves over Q that are defined by local conditions. That's the setting in which I've been working. And the other thing I should say about this conjecture is that there are no pathologies here. So there's no, the conjecture doesn't allow for any zero density family to contribute to the moments. In other words, if you just take the probabilities given here and compute the moments using the probabilities, you will get the formula on the second line of the conjecture. So we should expect no pathological behavior. Okay, so that's the conjecture for the distribution of Selmer groups. And I guess a lot of the progress that we have towards proving cases of this conjecture for the full family of elliptic curves over Q is due to the work of Bhargava and Shankar from 2013. So they determined the first moment of the size of the 2-Selmer group, 3-Selmer group, 4-Selmer group, and 5-Selmer group. I've listed the 2, 3, and 5 results here. So they find that the average 2-Selmer is 3, average 3-Selmer is 4, and average 5-Selmer is 6, as predicted by the Poonen and Raines heuristics. Okay. So some remarks about this result. It's stable under the imposition of quite general infinite sets of local conditions. So you get the same averages, even if you impose local conditions on your family of elliptic curves. It has a number of corollaries. So one of them is that because Selmer groups grow exponentially in the rank, the fact that the first moment of the Selmer groups is bounded implies that the ranks of elliptic curves over Q have finite moments of all orders. It's an interesting corollary. Now, the same cannot a priori be said about the sizes of p-Selmer groups. Just the fact that we know that the average size is bounded doesn't say anything about whether the higher moments of these Selmer groups are bounded. Now, from probability theory, there's an elementary inequality known as Markov's inequality. It says that if you have a non-negative random variable y, then the probability that y is at least a is at most 1 over a times the average of y. So you just apply that inequality, you get another corollary. So for each p that's 2, 3, or 5, and each rank r at least 2, we have that the probability that the p-Selmer rank is at least r decays exponentially in p. And of course, that bounds the probability that the rank of E of Q is at least r. I should also mention that the theorem of Bhargava and Shankar is for families of elliptic curves over Q defined by local conditions, but you could also consider other families of elliptic curves over Q, such as families of curves with marked rational points. And that's the work of Bhargava and Ho, where they compute these average sizes of 2 and 3 Selmer groups in those cases. Okay. That's the Bhargava-Shankar work and some corollaries. So now I want to focus in a bit on the 2 Selmer results. So in the case of 2 Selmer, the corollary that follows from Markov's inequality says that the probability that the 2 Selmer rank is at least r is at most 3 divided by 2 to the r. And as I mentioned, you can't rule out from this type of result the pathology where a zero density family of elliptic curves contributes non-trivially to the average. You just have that the average is bounded. So one potential situation that could happen is perhaps 100% of elliptic curves have 2 Selmer rank 0 or 1. And maybe the 2 Selmer ranks grow very fast on the complement, because if 100% of curves have rank 0 or 1, then that would mean that the contribution to the average from them is 3/2. So you need a zero density family of curves to contribute the other 3/2 to the average. So that could potentially happen. The other thing is you cannot deduce, for example, lower bounds on the probability that the 2 Selmer rank of a curve is some number r. Something that could happen maybe is that 50% of elliptic curves have 2 Selmer rank 1, and the other 50% have 2 Selmer rank 2. That would make a perfect average of 3. But that would mean that, for example, 0% of elliptic curves have 2 Selmer rank 0, which is kind of hard to believe. But a priori, we can't rule that out. All right. Now I want to tell you about the first main result of the talk, which is about bounding the second moment of the size of the 2 Selmer group of elliptic curves. So this theorem is from about 5 years ago now. So we showed that the second moment of the size of the 2 Selmer group is bounded. It's at most 15, and it's at least 10. And in red, I've put the Poon-and-Rain's prediction. So the Poon-and-Rain's prediction is that it should be 15. But we show that it is, in fact, at most that prediction. So this lower bound of 10 is quite trivial, actually. It follows from the fact that the average size of the 2 Selmer group is 3, together with the inequality 6 times 2 to the r minus 8 is at most 4 to the r. You just apply that inequality and you get this lower bound of 10. And the bound of 15 is tight, conditional on a tail estimate. We prove that you actually have equality. So 15 is tight. Okay, so immediately from that second moment result, we can apply Markov's inequality again and get a sort of exponential improvement on this upper bound on the probability that the 2 Selmer rank is at least r. We now have a bound of 15 over 4 to the r, as opposed to 3 over 2 to the r. Okay. Now that's Markov's inequality, but there's another inequality from probability theory called the Paley-Zygmund inequality, which states that if you have a real number, c, between 0 and 1, then the probability that a random variable y is at least c times the average of y is at least 1 minus c squared times the square of the average of y divided by the second moment of y. That's just a little result from probability theory. If you apply that to the setting, you deduce the following, which is that the proportion of elliptic curves with two-summer rank at least r is at least 26.66% if r equals 1. So 26.66% of curves have two-summer rank at least 1. And at least 6.66% of curves have two-summer rank at least 2. Okay, so these are more or less immediate corollaries of the second moment, first and second moment results together. And of course, because we've shown now that the second moment is bounded, we see that no zero density family of curves contributes non-trivially to the average size of the two-summer group. So you don't get that pathology, at least for the average. Okay. All right, so now let me tell you a bit about how we prove this boundedness of the second moment. Or how do you prove theorems like this in general? The main idea is to construct linear parameterizations of the Selmer groups so that you're able to count them. That's a kind of linearization trick. And for the case of two Selmer groups, there is a well-known result of Birch and Swinnerton-Dyer from more than 50 years ago now, which states that the two-Selmer group of an elliptic curve, y squared equals x cubed plus ax plus b, is naturally parameterized by orbits of integral binary quartic forms. So here the binary quartic form has coefficients a, b, c, d, and e. They're integers such that if you compute the two SL2 invariants of this binary quartic form, you have I of f and j of f are the two invariants. I of f has degree 2, j of f has degree 3, then well, I of f is supposed to be minus 3 times a, and j of f is supposed to be minus 27 times b. This gives you a orbit parameterization for two Selmer groups of elliptic curves. That's a result of Birch and Swinnerton-Dyer. It effectively linearizes the problem of computing Selmer groups, and it gives rise to the fastest known algorithm for computing these two Selmer groups, which I think is due to Cremona. Okay. So given that, computing the average size of the two Selmer group amounts to counting orbits of binary quartic forms. Now, there's a fundamental domain for the action of the group PGL2Z on binary quartic forms over R, so that every integral orbit can be represented uniquely as a point in this domain. And then problem amounts to counting these lattice points corresponding to these orbits. And that's a problem of counting lattice points in a Euclidean space. And for nice regions, you have Davenport's lemma, also known as the principle of Lipschitz, which says the number of lattice points is approximately the volume of the region. Now, of course, the trick is that the fundamental domain is not a nice region, and so you can't just naively apply Davenport's lemma to count points in it. And that's, in some sense, one of the main insights of Bhargava's thesis is a method for turning the fundamental domain into a region where you can sort of apply point counting results to it. So that's essentially how you prove the Bhargava-Shankar result in a very sort of reduced form. It doesn't at all do justice to the work, but that's a very brief explainer. Okay, so that's how you get the average. Why is the second moment different or more difficult than that? So via the parameterization, computing the second moment amounts to counting elements, pairs of elements, f and g, in the fundamental domain that share the same invariance, meaning they correspond to the same elliptic curve. So we're interested in two equations here. The I invariant of f should be the I invariant of g. The j invariant of f should be the j invariant of g. So these are equations of degrees 2 and 3 on our binary quartic forms. And so in other words, we need to count points on an 8-dimensional variety defined by the intersection of these two equations. It's a nonlinear variety, and that's a very hard problem in general. And the way we actually sort of circumvent this problem is that we show that the set of lattice points on this variety can be represented as the union of lattice points over an infinite family of lattices. And we count the points on these lattices individually, and then we sum over the lattices using equidistribution methods. That's very, very, very briefly how the proof of the second moment result goes. Okay. And in fact, our proof of the second moment result obeys quite a naive heuristic. That's why I want to explain this heuristic. So this can be seen as a sort of alternative to the Poon and Raines heuristics. You can use these heuristics to predict the Poon and Raines heuristics. So here's how the naive heuristic for the second moment of two-sommer goes. So you want to count pairs F1 and F2 of two-sommer elements of elliptic curves over Q. So fix F1. The first case is that F1 is the trivial element. And in this case, well, that doesn't say anything about our elliptic curve, and Bhargava and Shankar tells us that the average number of choices for F2 is 3. So from this case, we have 1 choice for F1, 3 choices for F2, yielding a contribution of 3 to the second moment. Now, the second case is where F1 is non-trivial. And in this case, Bhargava and Shankar tells us on average, there should be 2 choices for F1. But now we know something very special about our elliptic curve, which is that it has a marked non-trivial two-sommer element. And so we should expect that the two-sommer group of that curve will be twice as big on average. So in that case, the number of choices for F2 is not 3, but 2 times 3, or 6. And then if we combine the two, we get 2 choices for F1, we get 6 choices for F2, for a total of 12. And then adding up the contributions from the 2 cases, we get 15. You can actually use this sort of very naive argument to write down the formulas from the Poon and Raines heuristics in general. And in fact, our proof of the second moment result follows by sort of making each step of this naive heuristic rigorous. That's a very brief explanation of the argument. All right. Okay. So now I want to talk about a small generalization of this result on boundedness of the second moment. And we're going to generalize it by replacing the two-sommer group with the sommer group associated to a general sommer structure. So here's where I get to define sommer groups. So for an elliptic curve E over Q and a positive integer n, we have what are known as Kummer maps. So these are maps delta V from E of Q, QV mod NE of QV into H1 QV of the n torsion of E. This follows by just writing down the multiplication by n map and then taking the long exact sequence in Gauss cohomology. All right. And then we can define the n-sommer group, which is just a set of classes in H1 of En over Q that everywhere locally lie in the image of the Kummer map. That's the definition of the sommer group. And then we can generalize this with the notion of sommer structure. So a sommer structure is a collection of subgroups SV of E of the local cohomology, where SV of E is just the image of the Kummer map for all but finitely many places V. And then given a sommer structure, we can define a generalized sommer group, which is just the classes that map to SV of E everywhere locally. That's a small generalization. And then the same method of proof. Oh, before I say that, I should give some examples of what a sommer structure is. So some options for the sommer structure. You could just take it to be the soluble sommer structure. Namely, you take these subgroups SV of E just to be the image of the Kummer map at every place. That's the usual sommer group. Or, for example, you could take the unramified sommer structure. So you take the unramified cohomology everywhere locally. That's a valid sommer structure. So these are a couple of natural options. Okay. So we say that a sommer structure is subsoluble if the group SV of E lies in the image of the Kummer map for every place V. And under this condition, we can use the methods for our second moment result to bound the second moment of the generalized sommer group. Okay, so here's the form of our result. So there's some assumptions here. So we need to work with a family of elliptic curves that's defined by a large collection of local conditions. I'm not going to define what large means. It's just a technical condition. And then we need to assume that the sommer structure is subsoluble and acceptable. Also not going to say what acceptable means in the interest of time, but these are just some technical conditions. But under those conditions, we find that the second moment of the size of the generalized Selmer group is bounded by the following formula. So it's 1 plus 6m plus 8m squared. And m is a mass formula. It's a product of local masses. The local mass at a place V is an integral over elliptic curves over the completion at V. And what we're integrating is the size of the group S via V divided by the size of the two torsion of V. Okay. So these are the local masses. You multiply them together, and then you get m, and then that gives you this bound 1 plus 6m plus 8m squared for the second moment of the generalized two-Selmer group. All right, that's a generalization. Now, what we want to do is apply this result in interesting ways. So we're going to make specific choices of the Selmer structure to deduce corollaries of this theorem. Okay. Oh, I should also mention in this result we have equality conditional on a tail estimate. So this bound is tight. All right. So now I want to talk about the application of this theorem to studying two class groups of cubic fields. So a bit of a shift of gears here, but we're going to get this application by choosing the Selmer structure appropriately. That's the idea. Before I tell you about this application, I want to give you some background about what we should expect for the distribution of two class groups. So let's start with the Cohen-Leinster heuristics. So the distribution of class groups of number fields is an important problem that we care about. We want to understand this distribution, and in 1984, Cohen and Lenstra gave pretty definitive predictions for what that distribution should be for class groups of quadratic fields. I think it's fair to say that very few of these predictions have actually been proven. So actually, before Cohen and Lenstra came along, Davenport and Heilbronn determined the average size of the three torsion class groups of quadratic fields, and that agrees with the Cohen-Lenstra prediction. And then in 2007, Fourie and Kluners determined the average size of the four torsion, and was followed by Smith's work determining the entire distribution of the two-part. But beyond that, we don't really know anything. And now in 1987, Cohen and Martinet generalized those heuristics to number fields of any fixed degree, but with a caveat that their predictions about the p parts of the class group only work for good primes p. So I'm not going to say what it means for a prime to be good, but a reason for the prime to be bad is if it divides the degree of the number field because of Jean's theory. All right. Now in 2010, Mala realized that these heuristics of Cohen and Martinet need some adjustments to account for variations in the p parts of class groups when the base field contains p-th roots of unity. And quite recently, Sowen and Wood proposed the necessary adjustments that Mala observed were needed. Now, I have an asterisk here because the Sowen-Wood work requires an extra assumption that the prime p, if you're looking at p parts of class groups, the prime p should not divide the order of the Galois group. But it is expected that that assumption is not really necessary. So their philosophy should work even without that assumption. And I say that because in this talk, we're going to be interested in two torsion and class groups of S3 cubic fields. Here, 2 does divide the order of S3. So the Sowen-Wood heuristics don't immediately apply, but something like that should. Okay, so in this context, Mala makes the following precise conjecture. So when K runs through all isomorphism classes of S3 cubic fields ordered by discriminant, then the mth moment of the size of the two-class group over totally real K is given by this nice product formula, I equals 1 to m, 1 plus 2 to the I minus 3. And over complex K, it's similar. It's the product I goes from 1 up to m, 1 plus 2 to the I minus 2. Those formulas might look a little familiar to you if you remember the formula for the moments and the Poon and Rains heuristics. And there's a reason for that. Okay. All right, so I think only one case of this conjecture is known, and that's the case of the first moment, which is one of the main results of Bhargava's thesis, where he shows that the average size over totally real cubic fields is 5/4, as predicted, and over complex fields is 3/2. So I'll tell you a bit about the proof of this shortly, but the main idea is to leverage class field theory which reduces the problem to counting quartic number fields. And then Bhargava has results about parametrizing quartic number fields and counting them. So that's how the proof of this goes. And I should also mention in this context the work of Bhargava and Varma from 2015. So they prove a result about the narrow two torsion. So they show that the average size of the narrow two torsion over totally real cubic fields is 2. And the proof of that is quite different. So they use a direct parametrization of two torsion in class groups to prove this result. They don't follow the class field theory approach. And in fact, this direct parametrization can also be used to recover Bhargava's results on the average size of the two torsion. And the nice thing about these theorems is that the averages are stable under the imposition of finite sets or even quite general infinite sets of local conditions on your cubic fields. You still just get the same average. They're quite robust. Okay. Let me tell you a bit about how to prove these theorems. I'll tell you about the proof of Bhargava's theorem, for instance. So by class field theory, counting two torsion in class groups of cubic fields amounts to counting unramified quadratic extensions of these fields. And then there's a theorem of Heilbronn from 1971 that says that if K4 is a real S4 quartic field and K3 is the associated cubic field inside the Galois closure of K4, then the quadratic extension K6 over K3 that lives inside K24 is unramified precisely when the quartic field is nowhere over-ramified. And as a converse, every unramified extension, a quadratic extension of an S3 cubic field, lies in the Galois closure of a nowhere over-ramified quartic field. So here K3 is known as the cubic resolvent of the field K4. And the point is that by Heilbronn's theorem, it suffices to count these nowhere over-ramified quartic fields. And Bhargava has a parametrization of those. So his parametrization states that quartic number fields are in bijection with orbits of pairs of ternary quadratic forms over Z, and the group action here has two factors to it. So the first factor, GL2, sort of takes linear combinations of your ternary quadratic forms. And the second factor, SL3, is like a change of basis action on your quadratic forms. And yeah, so that's the parametrization, and then it becomes an orbit counting problem, counting orbits of this representation, which you can do by counting points in a fundamental domain. Okay, so that's how Bhargava proves this theorem. And now I mentioned that the averages are quite robust. They remain stable under the imposition of local conditions. That's very similar to the results for P-Sommer groups of elliptic curves. So it's natural to ask what happens when you impose global conditions on your family of number fields. So as I mentioned, for Selmer groups of elliptic curves, you could pass to like a family, a quadratic twist family, a very thin family, and the Poon and Rains heuristics still hold or are expected to hold. So you might expect maybe the same thing holds for these Cohen-Landstra type heuristics. So one example of a global condition you might impose on your number fields is the condition of monogenicity. So what's that? Well, a number field is monogenic if its ring of integers is Z adjoint alpha for some integer alpha. And a monogenized number field is what we refer to as a pair K alpha, where K is a number field and alpha is a monogenizer of it. And monogenized degree n number fields are in bijection with monic binary forms over the integers that are maximal in the sense that they define an integrally closed ring. So this is what we refer to as the defining binary form of a monogenized number field. Okay. So now if we want to talk about the statistics of these fields, we should put a height function on them. So in the case of a monogenized cubic field with a defining binary form given by x cubed plus ax squared y plus bxy squared plus cy cubed, we have a natural height function, which is just the maximum of two polynomials, I of f cubed and j of f squared divided by 4. So I of f is a quadratic polynomial in the coefficients, j of f is a cubic polynomial. And the reason that we use this height is that it is invariant under translation of the monogenizer by an integer. In other words, if you have a monogenizer alpha, you could just add some integer n to it. and that would also be a perfectly good monogenizer. And you want a height that is invariant under that action. And this height is invariant. Okay. All right. That's the notion of monogenized number field. And the story about class field theory and quartic rings has an analog in this context. And this analog is due to Wood and her thesis. So she showed that if you take quartic number fields with a monogenized cubic resolvent, then these are in bijection with PGL2 orbits of binary quartic forms. So that might ring a bell, because that's the representation that's used to parameterize two Summer groups. So it suggests that two Summer groups should be relevant in studying the two torsion and class groups of these monogenized cubic fields. Yeah. All right. So some remarks about the condition of monogenicity. We expect it to be rare. It is conjectured that 100% of number fields of every degree, d bigger than 2, are not monogenic, but I think this conjecture is not actually known for any d, surprisingly. And there's another nice fact, which is that a cubic field can be monogenized in essentially at most 10 ways by a result of Bennett. So the one thing that you might be worried about with these monogenized fields is that if you look at the family of monogenized fields ordered by the height function, it looks like cubic fields are represented many times in this family. You could have a cubic field that's potentially monogenized in many different ways, but by a result of Bennett, you can only do this in at most 10 ways. And so, in fact, we're only sort of overcounting cubic fields at most 10 times per field in some sense. We don't expect that this overcounting really has any impact on the distribution of the class group. All right. Okay, so then we have the following result that Bhargava and Shankar from 5 years ago. They determined the average sizes of the two torsion and the class groups of these monogenized fields. So they get an average of 3 halves for totally real fields, 2 for complex fields, and 5 halves for the narrow class groups of totally real fields, which is maybe surprising because these averages are different from the averages predicted by Mala, 5/4, 3 halves, and 2. So the proof of this follows the sort of class field theory approach, together with the Bhargava-Shankar results on counting orbits of binary quartics that they used for their two-Summer result. This theorem is also robust under imposing local conditions. The average stays the same. I should explain why the averages increase over the Mala predictions. There's some heuristics for this. So Hecke in 1981 proved a famous theorem, which is that the ideal class of the different of a number field is a square. And in particular, the set of square roots of the class of the different is a torsor of the two torsion in the class group. In my thesis, I suggested that if you look at a family of number fields on which this torsor is trivial, then you should have larger than expected average two torsion, and I gave some numerical and theoretical evidence for this. And then more recently, in some beautiful works of Siad and Shnidman and Siad and Venkatesh, they made this heuristic rigorous. So they showed that they exhibited precise mechanisms that explain why having a trivial square root of the class of the different torsor implies that the average size of the two torsion increases. Okay. So that's the case of the average sizes of these two class groups. But then using our more general result about second moments of generalized Selmer groups, we get the following result. So we find that the second moment of the two class group is at most 3. In the totally real case, in the complex case, we get a bound of 6. And for the narrow class group, we get a bound of 9. Right? These upper bounds are also tight, conditional on a tail estimate, and they're robust under the imposition of local conditions, so they stay the same. And I should say that these second moments are also larger than the Mala prediction. So Mala predicts 1.875 in the totally real case and 3 in the complex case. So we see that this condition of monogenicity not only impacts the first moments, but it also impacts the second moments. And these second moments, 3, 6, and 9, agree with the predictions of Siad Shnidman and Siad Venkatesh. All right. So how do we prove that? Well, the idea is to realize these two class groups as generalized two-summa groups, and then we can just apply our result. So we need to associate to every monogenized cubic field an elliptic curve in order to do that. And then we need to relate the two-class group of the monogenized cubic field to some generalized Selmer group of that elliptic curve. And we can do that using the unramified two-summa structure, at least for the two-class group. Now, for the two-part of the narrow class group, the unramified Selmer structure is not sufficient on its own, and we actually need to use two separate Selmer structures in conjunction with each other to get it. So that'll be an interesting wrinkle. And then once you have that, you can just apply the previous result on generalized two-Selmer second moments. Okay, so let's execute these steps. The first step is to construct an elliptic curve. So given a monic binary cubic form F that defines a ring of integers of a cubic field, we associate an elliptic curve EF by y squared equals x cubed minus 27 times that quadratic polynomial I of f x minus 27 times that cubic polynomial j of f. So that's it. That's the association. And this binary cubic form x cubed minus I of f over 3 xy squared minus j of f over 27y cubed. This binary cubic is equivalent to the binary cubic f under a lower triangular unipotent transformation over z adjoined 1/3. And then the way we get this cubic in the elliptic curve is just by scaling the y variable by 9 to get a short Weierstrass equation with integer coefficients. That's how we get that. Okay, so that's how you associate an elliptic curve to a monogenized cubic field. And now for the second step, what does the two-class group have to do with two-Selmer group? Well, we have the following basic result, which states that we have a monogenized cubic field with a defining binary form f, and EF is the associated elliptic curve. Then there's a bijection between the dual of the two-class group and the unramified cohomology of two torsion of EF. So how do you prove that? Well, the cohomology of two torsion of EF is in bijection with classes in k cross mod k cross squared that have square norm. And that arises from the fact that you can describe the two torsion of EF as the kernel of the norm map from the Weber restriction of mu2 down to mu2. Now, class field theory implies that this dual of the two torsion of the class group corresponds naturally to unramified quadratic field extensions of K. And then those field extensions correspond to classes in this group k cross mod k cross squared of square norm. And if you translate what the unramified condition means in terms of these classes, you get precisely the unramified cohomology classes. Okay, that's the proof of this correspondence. And once you have that, you just want to compute the second moment for the unramified Selmer structure. So we want to compute the masses in this case. So for the finite places, the masses are just 1. At the infinite place, the unramified cohomology has size 1. But the two torsion in the positive discriminant case has size 4, so you get a mass of 1/4. Two torsion in the negative discriminant case has size 2, so you get a mass of 1/2. And then the total mass is just 1/4 or 1/2, depending on positive or negative discriminant. And then using the moment formula, 1 plus 6m plus 8m squared, with these masses, you get 3 in the totally real case and 6 in the complex case. And that proves those upper bounds. Now, for the narrow two-class group, it's also related to Selmer groups. So via class field theory, the narrow two torsion is identified with what I'm calling H1F unramified of the two torsion of EF. So these are classes that are unramified at all finite places. And a local condition at infinity is problematic because in this cohomology group, a class could be insoluble over the reals. So in other words, you don't get a sub-soluble Selmer structure, which was a condition that was necessary for our second moment result to apply. But a key observation here is that if you have a class that is insoluble, well, you can just twist it to make it soluble. So in other words, we have a bijection in the cohomology between two torsion of EF and the two torsion of EF twisted by -1. And the image of an insoluble class under this bijection, the bijection in Galois cohomology, the image of an insoluble class will become soluble. So in other words, if you have a class that's insoluble for EF, it will be soluble for the twist of EF by -1. And then using this trick, we can actually write the square of the narrow 2 class group in the following way. So it's a sum of 2 terms. First term is the difference between the square of this generalized Selmer group for S tilde minus the square of the generalized Selmer group for S plus the square of the generalized Selmer group for S tilde applied to EF twisted by -1. Now, what are S and S tilde? So S is the unramified condition at all places. And S tilde is the condition that's unramified at all finite places, but soluble at the infinite place. Okay. So there was not one single subsoluble Selmer structure that captured the narrow class group, but by leveraging 2 different Selmer structures, we were able to capture it. So applying our methods, the first term in parentheses has an upper bound of 3, and the second term has an upper bound of 6, giving a total upper bound of 9. That's the proof of that theorem. I'm almost out of time, but getting to the end here. This method of proof for the narrow class group suggests that you can go beyond our bound for the second moment of generalized Selmer groups. You can go beyond it by leveraging quadratic twisting. So let's go back to the case of Selmer groups of elliptic curves, and let's see if we can use quadratic twisting to say more. The question is, can we leverage quadratic twisting in conjunction with our results on 2 Selmer moments to say more about the distribution of ranks and 2 Selmer ranks? Okay. So one thing we can do is look at the question of finding the average size of the 2 Selmer group of E cross E twisted by D. So in the case where D equals 1, this is just the second moment of 2 Selmer. But in the case where D is not 1, you get something interesting. And for example, if you look at elliptic curves of square-free discriminant and you take D to be -1, we get some interesting bounds. We find that the average size of this 2 Selmer group is at most 13 in the positive discriminant case and at most 15 in the negative discriminant case. So here we see that imposing the local condition of positive or negative discriminant actually has an impact on the average size of the 2 Selmer group, which is somewhat unusual. But what is this good for? Well, it has the following interesting implication. So I mentioned that the Bhargava and Shankar results imply that the ranks of elliptic curves have finite moments of all orders. But now with this result, we can say that if you look at elliptic curves over Q and ask about the distribution of the ranks of E over Q adjoin I, square root of -1, then that distribution has ranks. That distribution has finite moments of all orders. That's an interesting corollary thereof. But we can actually do a lot more than just this using quadratic twisting. And to state the final results of the talk, I need to make some assumptions. So here are the assumptions. So S is going to be a finite set of odd primes, and S bar is going to be the set of square-free numbers you get by multiplying primes in S. We're going to say that an elliptic curve E over Q is great if it satisfies the following helpful conditions. So E should have square-free discriminant away from primes in S. For each prime in S, either E or E twisted by P should have good reduction at P. The dimension of the 2 torsion of E of QP should be 1 for every prime P in S, and E should have good supersingular reduction at 2. All right, so those are the assumptions. That makes an elliptic curve great. Observe that greatness is defined by local conditions and that it occurs with positive proportion. In the remaining slides, we're going to restrict entirely to great elliptic curves. So every theorem is going to be about great elliptic curves. All right. So now we have the thesis of Ross Patterson, where he looks at the following. So instead of taking products of Selmer groups, he looks at intersections of Selmer groups. So what is the average size of the intersection of 2 Selmer of E with the 2 Selmer of E twisted by D? And he says for every D in the set S bar, you have a beautiful formula, which is 1 plus 2 to the power 1 minus the number of prime divisors of D. And in fact, his theorem is stated without this greatness hypothesis. I just imposed that hypothesis to get quite a nice formula. Okay. So then using the second moment stuff, we can generalize this result to the second moment, or extend it to the second moment. So for the second moment of this intersection, we get a bound 1 plus 2 to the 1 minus omega of D, times 1 plus 2 to the 2 minus omega of t, and a similar lower bound. All right. So all these results remain unchanged under imposition of further local conditions. For example, if you replace E by ED prime for any fixed D prime, you're going to get the same result. And these theorems give a lot of constraints on the two Selma ranks of the curves ED for D in our fixed set S bar. They tell you a lot about these two Selma ranks, but there's also more you can say. So using the greatness hypothesis together with Poitou-Tate duality, for example, you know that the two Selma rank of E differs from the two Selma rank of E twisted by P by at most 1 for primes P in S. And there's other constraints that Poitou-Tate duality implies. Okay, so my final result is going to be about taking all these constraints and putting them together and saying, what can you say about two Selma groups if you take all these constraints and put them together? So taking 6 primes for twisting, we get the following result. So we see that for every R from 0 up to 4, we find that a positive proportion of elliptic curves over Q have two Selma rank R. This is just by combining all the constraints that you get from averages, second moments, Poitou-Tate duality, everything put together. So for example, you see that at least 16% of elliptic curves have two Selma rank 0. And then there's other interesting things you can see by just staring at these percentages. So if you look at the odd parity, for example, you see like at least 48.7% of elliptic curves have odd two Selma parity. And you can look at even parity too. You get something like 42.8% of elliptic curves have even two Selma parity. And in red here, I've put the Poon-Reines predictions, so you can see how the bounds that we get compare to those predictions. So we're actually getting much closer for the odd parity than for the even parity. I'm not really sure why, but that's just a consequence. And then using these percentages, you can backtrack and say, well, what does this say about the moments of the distribution of the two Selma group? And for example, it implies that the second moment is at least 10.801, which is an improvement over the 10 lower bound that we had before. I think I've gone a little over time, but thanks so much for your attention, and thanks for the opportunity once again.